Hello, all. I felt bad about how discussion went yesterday and how a lot of you were getting very confused because I was going so fast, and also a lot of you couldn't see what I was writing. So I decided to make this video showing you how to do, normal acid-base titration, and then also how to do a titration with, a different uh, titrant and substance being titrated like what was in your pre-lab. So let's go ahead and get started here. Let me open up a blank screen and we can do some stuff here. Alrighty, and then let me make sure that my pen is working. And there we go. Okay, so I just wanted to reiterate, right, that a titration problem is in its essence any like any other kind of molar calculation issue problem that you get, right? So in a normal, what we call acid base titration, you always start out with what we call standardizing the base, right? And what that means is that you're actually going to figure out what the concentration of the base is, right? And then the second part, right? And then number two is then determining the concentration of an unknown acid. Okay, so those are essentially the two parts of doing any kind of normal acid-base titration. And acid-base titration is the one that you normally do anyway, right? So you'll be doing this a lot in Gen Chem 2, for example. Okay, so the first thing is to talk about then is standardizing the base. What does that mean? Well, the thing about sodium hydroxide, which is the base that is most used in acid-base titrations, is that you would think you'd be able to just weigh out how much sodium hydroxide you have, and put it in some water, and then you know what the concentration is, right? And in most cases, that's true for most solids. But the thing about sodium hydroxide is that it really likes water. And so it'll actually absorb water from the atmosphere. And you'll see these little pellets of sodium hydroxide. And they'll start out looking dry, but within seconds, they'll start looking like they're sweating. And if they're sweating, it means that they're absorbing water from the atmosphere and it's changing their weight. And if it's changing their weight, you can't get an accurate mass to be able to calculate what the actual molarity is of it. So even though a bottle will say something like zero point 0.1 molar sodium hydroxide, you still have to go in and do standardization of that base or that sodium hydroxide so that you can know what the actual exact concentration is. And the way you do that is you do a titration of that base, right, with a molecule called KHP, right? And so KHP stands for potassium hydrogen phthalate, right? Potassium hydrogen phthalate. I always forget how to spell it. Phthalate? Maybe that's how you spell it. Let me look it up real quick. I'm going to have to look up the molecular weight anyway, so I'll just go ahead and do that now because you have to know what the molecular weight is to figure out the number of moles of things are, right? So let me go ahead and type in here potassium on my phone. Potassium, hydrogen, 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 phthalate. I think I spelled that wrong because it's not coming up. I should have done this before I figured it out before I started recording. Ah, it's actually spelled like this. P H T H A L A T. Phthalate, right? And if you were wondering, its structure looks like this. Okay, so don't get confused with that P because that P does not stand for phosphorus. It stands for phthalate, right? And the phthalate is this part of the molecule right here. Okay, that's the phthalate part. And then here's the hydrogen part of the molecule, and here's the potassium part of the molecule, right? So don't get confused. That's KHP. And the reason why we use KHP to standardize bases is because it has this hydrogen here. We'll also call it a proton, right? Right, that it can actually be used to, just like an acid, right? It can be used to be given to the base, right, to make a, uh, a neutralization reaction where you add acid base together, you neutralize and get salt and water, right? And so the reason why we can do that with potassium hydrophthalate is because this is one of those acids, quote unquote, that you can actually weigh out and on a scale and figure out its exact mass, and not have to worry about it taking water mass from the atmosphere, right? And so um, most acids aren't like that, right? Most acids that you know are things like hydrochloric acid or sulfuric acid, and those things are actually gases. Hydrogen chloride gas will get dissolved in water, and that becomes hydrochloric acid, right? And so that's very hard to weigh, right? But potassium hydrophthalate is easy to weigh. Okay, and so the first thing to do then is to have a finished molecular formula. No, sorry, a finished or a balanced equation for the reaction, right? So KHP, right, plus sodium hydroxide makes you water plus sodium potassium phthalate, right? And so notice, right, we have here what we're calling our acid, which is KHP, and our base, sodium hydroxide, and we add them together in a neutralization reaction, and we get water and a salt, right? So always remember that neutralization reaction will always end up with water and a salt, right? And so it's already a 1-to-1 molar ratio because we have, um, we have two hydrogens right here, right? And we have a hydrogen here and a hydrogen here, so that's already balanced for the hydrogens. One sodium there, one sodium, that's good. One oxygen there, one oxygen there, that's good too. And then one potassium there, one potassium there, and then one phthalate ion and another phthalate ion, right? And so we have already a balanced chemical equation, so it's a 1-to-1 molar ratio, thank God, because that makes it easier, right? And so when you're doing an acid-base titration in the lab, what you have then is a burette. And here's the burette. At the bottom, there's just a little small little glass tube where the liquid comes out of, and then there's a little thing there called a stopcock that opens and closes to allow solutions to go through, right? And so here's the burette, and then below the burette is always, most people anyway, use a Erlenmeyer flask, right? An Erlenmeyer flask. And so the thing that the titrant, right, the titrant always goes into the burette. In this case, our titrant is sodium hydroxide. So when you're doing an acid-base titration, it's almost always going to be sodium hydroxide in the burette, and it will be the titrant, right? And just because I'm making this up as I go along, we'll say we have a 0.1 molar concentration, right, of sodium hydroxide in a beaker, right? Right. And so you have this beaker right here, and you're going to put that sodium hydroxide into the burette, okay? And you'll fill it up, and I recommend filling it up all the way to the top where the zero marker is. Okay, so where the line is 0, also known as 0 mils. Okay, milliliters. And then at the bottom here, what you'll do is you'll add in some KHP down here, right? And we'll say something like 0.5 grams of KHP. Okay, zero point 0.5 grams of KHP. All right, you put that in there. All right, you'll also add in some water as well. In there as well, some water, and it doesn't matter how much water you put in there because all you really care about is the number of moles of KHP, and you can figure out the number of moles of KHP since you have grams of KHP, right? Just from that, and its molecular weight, right? You don't need the volume of the water. And the other thing to notice too is that you're always going to put in an acid-base reaction 2 drops or titration, 2 drops of the indicator solution, which in this case will be phenol phthalate. Again, I don't remember how to spell phthalate. Maybe I should look that up too when I was looking up looking up the molecular. Sorry, how do you spell phthalate? That reminds me, though, I also need to know what the molecular weight of potassium hydrogen phthalate is because that's how we figure out what the molecular weight, the molarity. I mean, sorry, the number of moles is, right? So KHP's molecular weight is 204.22 grams per mole. Okay, awesome. Okay. So now you have your potassium, sorry, your hydrogen. Let me say that again. Your sodium hydroxide in the burette, and you have your your calcium, sorry, your potassium hydrogen phthalate or KHP in the flask. It's dissolved in the water, right? And what you're going to do is you're going to slowly open this stopcock right here. Slowly open the stopcock so that it starts to drip down the sodium hydroxide into the flask, really slow, right? And if you're lucky, you'll have a stir plate, right? It looks like a hot plate, except there's a magnetic thing in there, and it spins a magnetic bar, and it will stir it for you. But most of the time, you have to actually pick up the flask and stir it yourself. And you'll let it drop. You'll let the hydroxide drop into the flask until it turns into a very slightly, very light pink color. Okay. If you get to fuchsia pink, right, you've gone too far. So you have to make sure you stop when it starts to turn pink, right? When you see a light, very, very light pink color. Okay? And so when that happens, your level of sodium hydroxide will drop because a lot of it went down, not a lot of it, but some of it went down into the flask, right? So let's say it went down to, let's say 15 mils, right? So what that means then is that since you started at 0 mils, right, and you ended at 15 mils, it took 15 milliliters of sodium hydroxide to get the KHP to turn pink, right? Or in other words, that's how much volume it required to turn the KHP or get the KHP to its what they call the endpoint or the equivalence point, right? Where for every mole there is of KHP, there's an equivalent number of mole of sodium hydroxide. Okay, and so you started out with 0 mils here, and you ended with 15 mils. So that's super easy to figure out. What you put in there, right? How much sodium hydroxide you put in there. But if you didn't do that, say you start out with some different number other than 0, it's quite easy to figure out what it is. You just take the final volume that you have, right, and you subtract it from the initial volume that you have, right, and that gives you your total volume. So essentially, the 15 mils here is your total volume that went into the flask, right? Because 15 minus 0 is 15 mils, right? And so when you have questions like titration questions and it says something like it took 12.5 milliliters of so and so to get this substance to its endpoint, that's what it's talking about. Okay? Okay, so that's good. So now that you have all that figured out, right? Now that you have all that figured out, you've got to figure out what the actual concentration is then of the sodium hydroxide, right? Well, how do you do that? Well, you've got everything you need right here. Okay. First, you do your molar calculation, right? So you had zero point 0.5 grams of KHP, right? And for every mole of KHP, right? For every mole of KHP, we put there the molecular weight, which is the 204.22 grams, right? And some of you may be asking yourself, where the heck did I get the 204.22? You could get one of two ways. You can ask Siri what it is, and Siri can tell you, or you can look on the periodic table and figure out and add up all the different molecular weights of the potassium, the hydrogen, and then all the different atoms that are inside the phthalate ion, right? And they both will give you the same answer. Okay, that's right. Okay. And then the next thing to do is to look at your balanced chemical equation here, and notice that in the KHP sodium hydroxide equation, it's a 1-to-1 molar ratio, right? For every one KHP, you have one sodium hydroxide, right, that reacts. And so now you can say for every 1 mole of KHP, you get 1 mole of sodium hydroxide. Okay, and so that's great. And the reason why that's great is because when you get moles of sodium hydroxide, after you get moles of sodium hydroxide, you can actually then use the volume of sodium hydroxide that you put in there, right, to figure out what the concentration of sodium hydroxide is, right? So let's do this math real quick. And I've got my handy dandy calculator right here. We have zero point 0.5, and then you multiply that by all the numbers at the top. So it's zero point 0.5, right, times 1, which is just zero point 0.5. And then you divide it by all the numbers at the bottom, which is the 204.22 times 1, which is just 204.22, divided by that. So zero point 0.5 divided by 204.22, and I get the number of moles of sodium hydroxide to be 0.0244 and a whole bunch of numbers, right? And we'll just leave it that way for now, okay? And so just remember, the reason why I do this, do the dimensional analysis to do this, is because I can very easily go in, just like we do when we do metric conversions and all kinds of other conversions. I can cancel out grams of KHP, right, with this grams of KHP down here. Sorry, I forgot to put KHP right here. This grams of KHP right there. Then I can cancel out moles of KHP, right? And now I'm left with moles of sodium hydroxide, which is what I needed, right? This is what I needed. And so now I have 0.00244 moles of sodium hydroxide. That's great. You know why? Because I have a volume of sodium hydroxide now, right? And recall that concentration or molarity. So don't get confused. The most common unit for concentration is molarity. Okay, so people will say concentration is C or CO and C for concentration, right? They'll use it interchangeably with M for molarity or molar, right? And so the equation is this: number of moles, not number of moles, molarity, right, or concentration equals the number of moles divided by the volume in liters. Okay, and so you've already figured out what the number of moles is, right? You did it right here, moles of sodium hydroxide, right there, right? And then what is the liters? You've already figured that out too. That came from the burette. That's right here, the total volume of the burette. The only problem though is that it says liters of volume, not milliliters of volume. So you have to remember to convert the milliliters of volume to liters of volume, which is as easy as this, right? So if you have 15 mils, right? If you have 15 mils, sorry about that. If you have 15 mils, right? To convert it to liters, all you have to do is move the decimal point 3 spots, like so, right? So that means there's a 0 in front of the 1 now, and there's a decimal point. So 15 milliliters to 15 milliliters to liters means that it is going to be 0.015 liters, right, for your total volume, right? Good stuff, good stuff. Because now you can say molarity equals the number of moles of sodium hydroxide, which here is 0.00244 moles of NOH, and then divide that by the 0.015 liters, right, of the sodium hydroxide that you put into the flask, right? So you do that calculation, 0.00244 all right? And I know that the number went really far. You had a very long repeating decimal. I mean, 5 digits is plenty for this, all right? And then divide that by 0.015. And so I get then molarity or concentration, right, of sodium hydroxide is actually not the zero point 0.1 molar that was written on the bottle, but it's actually 0.16266 and a whole bunch of more repeating decimals molarity, right, molar of NaOH. And so that number right there, the actual concentration of sodium hydroxide, is very important when we get to the second part, right? Where we're trying to determine the unknown acid. Okay, where we're trying to determine the unknown acid. And I will put that part in a separate video. That way you don't have to fast forward and find the right one. And then I'll put the third part where we're doing a titration with some other compound like EDTA and copper chloride. And so there'll be 3 videos, one on the standardization of the base, one on determining an unknown acid, and the third one will be the one on how to do a titration with something other than an acid and a base. Okay, and we'll use the example of EDTA, which is ethylene diamine tetraacetic acid, and copper chloride. Okay, so I'll be back in the next video. I will see you there.